Hello, and thank you for the invitation to present today at this prestigious meeting. I'm very honored to be here. My wife and I have experienced our first visit to Japan and are extremely impressed with your culture as well as your hospitality, so thank you very much. I'd like to present a paper that a presentation is supported by a white paper that is fully available to anyone here who would like a copy. There's nothing secret or proprietary. Everything I discuss today is intended for open use. And in fact, all our work that we're doing, even though we are a commercial company, we intend to make fully open and available to the world. We think, first of all, it's important work, but also we think that our projects and our work will be improved by sharing and not worrying about protecting intellectual property and concepts. It's a very sort of academic way to go about doing business, which I believe is the future for all of us. So I'm presenting 10 slides here, very basic and high-level concept slides. But I will deliver deeper information as I go during the presentation. So rather than talk about electricity and microgrids and power system architectures, which I've spent 32 years working on in the United States and worldwide, I believe we need to look at a much more complete solution to our energy problem. That simply producing electricity is a first step, but it is not a proper way to think when we start looking at the problems that we're facing in the world due to our ever-increasing population and our limited natural resources. So while I think production of electricity is a very important topic, I think it's only a very small piece of a bigger systematic problem that we have as a world. And I think we need to address the complexity of that problem in a very thorough and systematic way. So what I'm presenting today is an all-systems approach to dealing with energy, with a focus on economics, not on technology. So I apologize in advance because I know this is a highly technical meeting. And I've presented many technical papers during my career. This is not a technical paper. This is a business paper on how do we actually move forward as a world economically with an economically sustainable approach, recognizing that we cannot ignore environmental sustainability if we're serious about economic sustainability, that they are in fact linked if we're being honest. So when we say all systems approach from a building's perspective, we're talking about mechanical systems like heating, ventilating, and air conditioning, electrical systems, even plumbing, and communications. So rather than just look at electricity, we're looking at them all. And what our goal is to collapse these systems into one integrated solution and eliminate unnecessary overlap of equipment, of complexity, and of consumption of energy. We think this is very important if we're serious about reducing our total energy consumption, not just electron production. So let me just take a little bit of time here to talk about AC systems versus DC systems, the Tesla, Westinghouse, war of currents that happened 100 years ago, versus a hybrid system, and what the pluses and minuses of these approaches are. And again, through the lens of economic sustainability, how can we actually build these systems, deliver them, and change the world now, rather than something that could happen in the future? And I also want to add, before I continue, that everything I'm talking about has already been done and is running in commercial applications now in the US and in the Caribbean. So these are actual delivered, commercially functioning systems, and the results that I put here, I skipped the math and just went to the conclusions. It's all supported by measurements. So it's not theoretical, it's factual, measured results. We plan to publish a series of 5 white papers, this one being the high-level white paper, and then following with more detail across various applications. So when we look at the loads that we all are dealing with today on a residential level and on a commercial level, but not on an industrial level, we look at these types of loads: electronics, motors and pumps, lighting, appliances, and power electronics. I separate power electronics because I'm talking about power electronics from a systems level perspective versus user electronics like televisions and audio equipment, et cetera. So these are the primary loads that we're dealing with today in homes. Really, it covers everything. Because when we talk about pumps and motors, we're talking about HVAC systems, we're talking about geothermal systems, we're talking about many different technologies all run off these basic components. So if we look at these things from purely a systems level perspective and how they work with each other, we're going to come to some conclusions that are really quite obvious after we look at them this way. When we look at efficiency of an AC grid system, as we have now pretty much worldwide, we have a very, very, almost embarrassingly inefficient electric delivery system. If a factory ran this inefficiently, it would have been out of business 100 years ago. Would have never made it. And I think the problem is, myself being a power system engineer, practicing power system engineer for 25 years, being very involved in building the US grid, energy management systems, supervisory systems, on and on and on, and working in Europe and Southeast Asia and other places, we all looked at it as though the centralized power plant architecture was obvious, and we didn't question that. We simply built it out and then tried to optimize and manage that system as best as possible. But clearly, that has outlived its usefulness, that architecture. Because the simple numbers say that the best efficiency we're seeing is 50%. And I'm talking about from the time we dig up the coal in the ground and the energy it takes to dig that coal and bring it up to the surface of the earth and transport it to the power plant, generate the electrons, transmit the electrons through the transmission system, through transformers, through the distribution system, out onto the streets and into the loads. Electron to lumen, if you want to say that. 50% is generous. 35% is probably more realistic in the vast majority of applications. So who would design a system like this? No one would design this system today, knowing what we know. Our best example that I know of a hybrid system, and that inspired me to look at these approaches that we're talking about today, is the Toyota Prius. A colleague of mine, Bill Reichert, was one of the key designers of the Prius architecture. And Toyota really led the world, in my mind, toward an example of a truly efficient, intelligent way to manage a power system. And I don't see the difference between that Toyota Prius and what our power systems should look like and operate like. today, that's not reaching for the future. That's where we should already be. And I feel we have not gone there for many wrong reasons, mostly political and not technical. So these arguments that I'm making, I'm stating that we can quickly reduce the electric load globally while we, at the same time, provide energy access to the developing world. We can simultaneously reduce the global energy consumption by 50% if we started now, without new technology. Now, I couldn't have said that 3 years ago. There have been some significant power electronics breakthroughs in material science and power electronics. But I can say it now because we've done it on live systems, ranging from homes to commercial complexes and now industrial applications. So this is something that is realistic and economically sustainable. So the hybrid system, I think, that is impressive and really moved the world in a new direction is the Toyota Prius architecture. But then I look at DC systems and what we're doing with our systems today, and I even see better results. Not necessarily a ubiquitous solution, but where these pure DC systems can be installed, we can see 90% plus efficient systems, electron to lumen or electron to load. 90% plus we have now running, not lab, in the field, commercial applications, running buildings. Imagine that, 90% plus. Now, what excuse do we have? We don't have an excuse anymore. We only have politics stopping us from accomplishing this. And by the way, everything I'm talking about, open source, open architecture, standards-based solutions, off-the-shelf equipment, nothing proprietary to my company. My company is an energy project developer. Our job is to go build energy projects that we can finance and own and operate for 20 plus years. So I have no interest in technology. I have interest in projects that work, that can return an investment to investors, and can be self-sufficient and energy efficient. If technology is what I need to get, the tool I need to get there, then I'll use it. That's how I see the role of technology. It is a tool, an enabling tool. It is not the end result. So the basic concepts that I'm talking about here is applying DC to all possible electric loads, avoiding and preferably eliminating the need for any conversion of the current to alternating current. It's not realistic on some cases. Certainly in homes, you're going to need some what I'd call legacy convenience outlets for the AC system. And I think we need desperately to look at the system that we have now as a legacy system that we're stuck with, and that we need to get away from as fast as possible. As fast as possible, maybe 10 years, but no longer. There's no reason why it should take longer. So in the meantime, DC-based systems give us a huge advantage of electric storage with a very high efficiency. If we convert to AC and use storage on an AC system, we lose those benefits. A hybrid system really does not work well in a stationary application economically. And let me just pause for a second here and think with me about this. We build a new building. We all decide to go build a new warehouse together. All of us in this room. We walk in, we say, okay, what do we need to do to build this new building? And typically, in the construction industry, the first thing we do is install AC power on the site so that the construction team can come in and run their equipment and build the building. Starting with pouring the foundation, framing the building, etc. That cost if you actually honestly look at it, from electron to load, is extraordinarily high. And it's simply hidden from us because we have a grid, we have power plants, we have fuel delivery systems, and we're just tapping in at that site. But even considering all that, we're typically spending on a commercial building in the United States about $100,000 to do that. Now that includes the connection to the grid, the transformers, the panels, the switching, the protection, the switch gear. That's a lot of capital right up front before we can start building our building. So the utilities in the United States recognize this. And so now what they're doing is they're saying, if you want us to put AC on your site to do your construction, you need to sign a 20-year contract with us for the supply of that power, or we won't do it. That's a problem. So we need to step back and ask, why would we sign that contract? How is that contract good for me as a business person? So if we look at the basics of these systems and ask ourselves, do we need that AC on that site from that grid? Do we really need that much power? Do we really need 1,500 amp service for a commercial building today? The answer is absolutely not. Not anywhere near that number. So why are we doing it? Because remember, when we do that, the electric utility company now is obligated to supply that 1,500 amp service 24 hours a day for the next 20 years or however long you have service on that site, at least 20 years. But if you only use 100 amps, the electric grid system still needs to support 1,500 amps, which means we're generating that much extra power all the time, by law, in reserve. So we have a function called spinning reserve on our power systems worldwide, just so that in case all of us wake up in the middle of the night, turn everything on that we could possibly connect to our system, the power system could supply it. And that's by regulatory requirement in most developed nations. So I suggest we challenge that notion and we start right away changing that paradigm. And the enabling technology is electric storage. So if we use electric storage in the form of DC, we have a very, very efficient storage system. And we eliminate AC distribution inside buildings. We can easily build simulated models of buildings, even at the level of private architects. It no longer requires a university to run simulations if you're doing DC, because they don't have any phase relationship problems. We have no transient issues to speak of. We have minimal transient issues. Our protection scheme is incredibly simplified. Fundamentally, we're designing our system using Ohm's law. And because of that, if we look at Ohm's law and we look at Kirchhoff's law together, we understand this is simple. This is math we can do in our head. This is math, most importantly, that engineers and architects can do everywhere. Doesn't matter about language, it doesn't matter about any of these things. So simplifying that architecture translates to faster delivery of systems, and I'll even argue safer systems. And then we can optimize the building architecture around the systems themselves. What I mean by that is, for example, in a geothermal system, we can pour the foundation more intelligently so that we can actually integrate the geothermal system into the foundation structure and make the foundation a component of the geothermal system. Functionally, it would become, in a cold climate, a heat sink. So we're doing that. And I'll talk about some of those examples shortly. The important thing I want to say is that these concepts and these system designs have been enabled by some breakthroughs that simply were not available until recently. I think one of the most fundamental breakthroughs is the application of post-silicon switching devices, such as silicon carbide and gallium nitride, to insulated gate bipolar transistors, IGBTs. IGBTs were invented almost 20 years ago by a colleague of mine, Jay Baliga, who's a professor at NC State University in Raleigh, North Carolina, and now is used in about 300,000 products worldwide. And one huge advantage of post-silicon-based IGBTs is we can switch much higher currents much faster than ever before and efficiently dissipate the resulting heat. That's a big deal when we're trying to install DC systems. So without that, devices like MOSFETs that have been used up until now wouldn't be able to handle the currents that are required to drive the inrush current requirement of motor starts, for example, would pretty much make the system fail too often. The maintenance would be very high. So I think that IGBT is a key breakthrough. Clearly, another key breakthrough that's sort of obvious and not listed is the internet. And what I mean by internet is not necessarily the public internet, but the internet technology that enables us to manage and integrate solutions seamlessly with very high bandwidth and excellent reliability. So internet technologies I'll throw into a bucket of just generally automation and communication functions that are now off the shelf and inexpensive and simple to do. Where as recently as 5 years ago, we would need specialists to install routers and switches and configure our communication systems on high-speed networks that are high reliability architectures like power systems and all systems approaches. These systems would be very expensive to integrate because the communications was too complex. But now, that's just not the case. It's honestly trivial. And that's exciting because now we can start looking at all these different functions that are available and reduce them to the home, to the commercial building like this building, to these lights. Those are LEDs there. But I noticed, I'm a little surprised, in Japan I didn't see more LED lighting. It's in the last 18 months in the US, we went from 80%, 18 months ago, 80% of the lights sold in the United States were fluorescent lights. And today, 20% are fluorescent lights, 80% are LED in 18 months. And the reason is the economics work. I mean, we can change out, I'd be happy to come to this building and change out this building. I could do it very inexpensively, quickly. Return on investments, about a year. But what it means to the grid for Japan, if you look at all those train stations I've been running through on Japan Rail and all the fluorescent tubes, we're talking about a reduction of 75% on your lighting load on your system. That means you don't need those power plants that you plan to bring online. Maybe controversial to say, but it's true. So if we look at an advanced society like Japan, where it's clear to me that you live very symbiotically, you live very closely together with a lot of respect, I think it's critical that the management of your resources is optimized. And I know you know that. It's clear as a culture that you know that. So to me, those things that can be quickly done, that have a return of investment of a year, just on the cost to the user. I'm not talking about the government involvement. I'm talking about private businesses getting a return on investment in 1 year by changing out their lights. The net effect to the government and to the country is a 75% reduction in your electric light load on public lighting as well as on all private lighting. It's an obvious thing to do. And we need to do it worldwide. We need to do it in the United States. We need to do it in China. I met with a delegation from China in Washington, D.C. a couple of weeks ago. The State Grid sent a delegation of 20 people. And we had an excellent session. And we can see China is moving very, very rapidly in this direction because the economics work. I think the complexities of climate change and the complexities of the politics associated with coal and fuel delivery and uranium mining, and et cetera, can be eliminated, completely ignored by the economic value of this to your businesses and to your profitability of your country. It can be driven at the personal level because you own a business and you want to improve your profit. Do it. There's no reason not to. In fact, there's every reason to do it. So when we look at these technologies, another major breakthrough technology is lithium titanide oxide batteries. Thanks to Toshiba, they have put into production what we in our National Science Foundation lab in the United States believe is a product commercially available that changes the world. The electric storage problem has been eliminated by that technology. I know that's a big thing to say. I don't own any stock in Toshiba. I'm not commenting on their management. I'm not worried about what their company is doing. That technology is fantastic. I know they're in the news. I saw that yesterday. But that doesn't matter. The technology is fantastic. And the engineers in Toshiba need to be on the front page of the newspaper, not the managers, obviously. But in any case, what we're seeing is a battery that could last, the way we're using it in buildings now, we believe it will last up to 100 years. 100 years. So while it is about twice as expensive as the equivalent lithium iron phosphate battery that the world has been using, it might last up to 100 years with the proper management. How exciting is that? We talk about generations, next generation. How about this generation? How about we do something now? We invest in a battery that we could leave and inherit to our ancestors. Now, economists will tell you that it makes more sense to buy the lithium iron phosphate battery for half the price because 10 years from now, there'll be yet another better solution. I argue against that from a systems level thinking. That's not good thinking. It's good thinking if you're just going out and buying a battery. It's bad thinking if you're thinking about it as a system, because if you can design a power system solution that can power your home today and consume less than 50% of what you're consuming now without giving anything up, same amount of light delivery, maybe better, same comfort level for your air conditioning. If you can deliver that system today and keep it for 100 years and leave it for your relatives, I think we're fools not to make that investment. And whether it's Toshiba or it's someone else, lithium titanide oxide has been around for a long time, but Toshiba has perfected the process of manufacturing it and driven the cost out enough that we can finance it on a 20-year project. So frankly, we're not worried if it lasts 100 years. From a financing standpoint, if we can install solar and batteries and it lasts 20 years reliably, you know, that's what we finance. The world doesn't really look at 30 years, 50 years, 100 years, but we should. And if people in your minds are thinking this is crazy, there's plenty of evidence of this very idea in the form of the Tennessee Valley Authority in the United States. TVA built hydro dams during the FDR years. And the hydro dams were built at significant capital cost, but they were built so well that they're still producing power at a little over 2 cents a kilowatt hour today. So that investment was made. Every 20 years or so, they revamp the turbine gensets in these plants and continue to use the dams. They do require some maintenance. The 100-year power system approach at a central level has always been fundamental. You know, 50 years is the expected life of our power plants. So, and our nuclear plants, of course, have to last much longer because otherwise, what do we do with them? So the natural thought is, how do we reduce our power system design to the same competitive status with the centralized power system? Can it be done? The answer has been no until recently. But now not only is it done, but we're actually getting 5 nines availability on our system, plus. So 99.999 plus % of the time, we will deliver power to the load on a local generation system. So there's case studies. These are 3. There are many now, and growing at a rate that myself and my colleagues have never seen. We started with a resort up in the high Rockies in a terrible climate where it gets to be minus 40 degrees during the wintertime with 400 inches of snow. So hard to believe. It's one of the worst climates in the continental United States. And it's also at an altitude above 8,000 feet. So very difficult. The site is huge and impressive and world-class. And the consumption on the site is about 1 megawatt peak load when we started, which was a year ago. Today it is about 750 kilowatts. However, a new lodge came online since we started. So that would be about 1.2 megawatts, down to 750. And by March, we'll be at 500 kilowatts on about 250,000 square feet under roof, spread across 6 facilities. And these are very high-end guest ranch, resort, hotel, set for skiers in the high Rockies. So we're cutting the total electric load on the site by 50%. We're cutting the grid load by 90%. So we'll only be buying 10% of the power from the grid. We could disconnect, and we may disconnect, but we're being conservative initially. And a side note on that, the grid in this location is only 4 nines available. So for anyone who has studied statistics, you know if you put a 4-9 system on a 5-9 system, you reduce your availability by connecting to the grid. So statistically, it makes sense. But there's no hurry because the system architecture supports a gradual change out. And the economic effect of this is producing a return on investment of somewhere around 10% internal rate of return. In other words, after we invest all the capital and do all the work, and this is all the engineering, everything captured, no subsidies, no tax breaks for solar, no anything, just cost. We're returning to the investor a 10% internal rate of return. Not very hard to sell that. And this will be a site that we expect to be #1 eco-village, eco-resort in the world. So not only was there no added cost, we actually gave them a return on investment on the capital invested. Another very important thing is that the cost of electricity on the site will be flat for the duration of the life of the system, regardless of fluctuations in fuel costs. Because we're only using 10% grid, we'll have a minor fluctuation there, but we also are going to offset any potential costs of that if we stay connected to the grid, which we likely won't. But if we do stay connected to the grid, we will offset any of those fluctuations in costs of that last 10% of grid fossil-based electricity by efficiency improvements. So I'm going to invoke Moore's law, which I'd call more Moore's trend from the electronics world, and say that it's very realistic that every 18 months we will lower the energy use on our facilities by 20% indefinitely. And that seems ridiculous, but if we ask ourselves about the LED light bulb and we look at the cost and we look at the reduction in load on an LED light bulb, we're seeing those results for the last 10 years. For some reason we've ignored it, I don't know why. But we need to embrace these thoughts because they've turned into economic indicators that this is viable without subsidies now. So we have a responsibility to do this. And it's independent of climate change and independent of these fuel issues and independent of the politics, because it comes down to just simple business and math, that it would be irresponsible for us as business owners and as private citizens to just throw away money. I don't know anybody who wants to do that. So when we look at these three projects, they have similar functions. In the case of the city of Boulder, Colorado, we're doing a water plant, water distribution plant. And in this case, we're reducing the total load on the site by 75%. And we're switching the entire site to DC power, off-grid, for 20 million gallons a day of water production for the city of Boulder, Colorado. It's one of two water plants. And one of the innovative things we're doing there is we are using the water system itself as a part of the storage system. So we'll pump water into the system using solar when solar is available. Even if there's no consumption, we'll make sure the levels of the water system are maximized so that we can take advantage of the solar and use it as a battery, essentially. So these are system level thinking that we're doing. I need to just close up here. I'll skip the planning process. Scaling the system approach is fundamentally driven by education, first and foremost, building a workforce, which is very easy to do because if you're working with DC systems, every auto mechanic in the world works on DC power systems every day. And it can easily be cross-trained to work on these systems in your home. So the gentleman with the last presentation on the idea of using the car as an electric distribution system for stationary applications is exactly agreeing with this. We're saying, why not power your home from the car instead of your car from the home, or vice versa? And so that education is very important, the workforce. And then tools for practitioners, for people who actually go out to do this. What are the tools required and what is needed so that they can effectively come out to your home, to condo complexes, to industrial sites and rapidly install these systems to meet safety requirements, et cetera. So summary conclusions. We can reduce the electric grid consumption by about 80% with this approach. And the only thing stopping us is the will of us as individuals to do this. I'm dead serious here. For example, if you use DC at under 50 volts DC, it's touch safe. Under 50 volts DC. At 100 watts, does not require a licensed electrician by National Electric Code. You can go do it yourself this weekend. Don't have to pull a permit. You don't have to ask the government. You don't have to talk to your utility. You just go hook it up. Completely safe and can't cause a fire. It's actually in our National Electric Code, 2014. And there's no record of a human being electrocuted by any voltage under 50 volts, including people with heart problems and pacemakers. So the day of danger of our electric system should be already over, yet we're not doing this, and there's no excuse for that. So reducing the electric consumption on the grid drastically, the total load by about 50%. HVAC consumption, we'll hear a presentation on geothermal. We're seeing excellent results with geothermal and installing it heavily. Certainly greenhouse gas emissions are, potentially, well, they're drastically minimized because especially if we are in a high solar content area, and especially if we adopt these efficiency measures. There's every reason to believe that we can, the only issue we have is producing the silicon wafers themselves and the energy that it takes to do that, which has now become quite efficient. And I should also note that about 20 years ago when I first looked at solar, it took over 5 years to recover the cost of making the silicon wafers. Now it's under 8 months. So that whole world is changing very rapidly as well. Again, tracking the Moore's law of technology and technology development. And so we look at these electric shock and fire hazards in the developing world. I've worked heavily in Haiti after the earthquake and been there many, many, many times. And I'm working in the developing world in Colombia and other places. We look at all these things and they are clear that safety is critical. Resiliency is improved with the higher availability. And then finally, that stabilized cost for 20 years. So that concludes my presentation. Thank you.